So in our previous discussions on fluids, we were considering the cases where fluids are just sitting there statically, and we were talking about things like density and buoyancy for fluids at rest. Of course, fluids aren't always at rest, so we need to take a look at what happens in the case where we have fluids in motion. So to consider those cases where fluids are moving, we can only do that and come up with a theoretical treatment of it in the case where we have what we call an ideal fluid. So the ideal fluid has some properties which we'll discuss. First of all, the ideal fluid is non-viscous. That means that there's no internal no internal friction forces operating on the different layers of the fluid. This is one of the conditions which is probably not often met very well for a real fluid. However, if you have a fluid moving through some sort of container or some sort of channel, whether it's a river or a fluid moving through a pipe, for example, if you're far enough away from the boundary, then this approximation of a non-viscous fluid can be close enough to ideal that we can consider it to be true. But in general, most fluids have some sort of viscous force operating on them, and it's very hard to find a fluid that doesn't. But nevertheless, it's one of the conditions we need to make our equations work, so we'll consider it to be true. Secondly, the fluid has to be incompressible. That is, if you apply pressure onto the fluid, the density of the fluid should not change. So most liquids that we deal with, water for example, or oil, most of the liquids are very, very incompressible. So this approximation is easily met for most liquids. However, we want all of our equations to work for all fluids, and we'd like our to consider fluids that are not only liquid but also gases. And most gases are highly, highly compressible. So this condition, although it works for fluids that are liquid, it does not easily hold true for fluids that are gases. So if our fluid is water, for example, this is easily met. If it's air, nitrogen, hydrogen, any other type of gas, then this condition is not easily met. The flow of our fluid has to be steady. That is, if you pick a certain point in space and stare at that point, all the properties of the flow should be the same. So the velocity at that point should remain the same. The density should stay the same. The pressure should stay the same. All those properties at that particular point in space should stay the same and not change in time. And then finally, the flow should be laminar, that is to say, not turbulent. In other words, the flow should be smooth, right? So if you watch the fluid flowing, it should flow smoothly throughout its path. Now, it's fairly easy to get a fluid to flow smoothly initially, and if the velocity of the fluid flow is low enough, you can often hold the flow to be laminar for a while. But it's very hard for fluid to maintain that laminar fluid, especially if it meets any sort of change in the path, like a bend or a change in pressure or something like that. So laminar flow is approximately true, and we can establish a laminar flow, but to maintain laminar flow is relatively difficult. Although we're considering our ideal fluid, so we can do anything we want with our ideal fluid. All right, so let's look at a case here where we have a fluid contained in a pipe, and the pipe changes diameter. So it changes from a small diameter to a large diameter, and it also changes height. All right. Since our fluid that we're considering is an ideal fluid, it is incompressible, and so whatever, if we look at our pipe and we pick a chunk of time through which our fluid is going to be flowing, and that time is represented by the fluid contained in this length here, because the fluid is incompressible, there is a conservation of mass that has to be maintained through which the fluid flows through the pipe. So it turns out that, and your book has a good derivation of this, but what we get is a continuity equation that is expressed as this. The cross-sectional area of our pipe, that's this area here. If the pipe is rectangular, you can find it the height times the width. If the cross-sectional area is a circular, then it's just pi r squared. But the area times the velocity of our volume flowing through here has to be equal to the cross-sectional area here times whatever the velocity is here. So if the area has increased in this region, then the velocity in this region will have decreased to maintain the continuity. Then if we apply the conservation of energy to the fluid, we come up with Bernoulli's equation. So this is Bernoulli's equation. The left side is the same as the right side, and we've just taken into account, you can think of this as the initial case and the final case. So we're saying the sum of the total energy has to be equal to the sum of the final energy. Although really we're not dealing with energy in this case. In this case we're dealing with pressure. So the initial pressure plus 1/2 rho V1 squared plus rho G Y1, the height here, has to be equal to P2 plus 1/2 rho V2 squared plus rho G Y2 squared. So the density doesn't change. Again, the fluid is incompressible, but the pressure can change, the velocity can change as we've already talked about, and then the height changes. So this is just the pressure of the liquid at this point. This is the pressure of the liquid at this point. This term here is related to the kinetic energy. This is the final kinetic. This term is related to the final kinetic energy, and then this term is related to the initial potential energy, and this term is related to the final potential energy. All right. Now note, though, you should check the units. This is density. Density is mass over volume. So mass over volume times a velocity squared. You should check to make sure it has the same units as pressure. All of these terms have to have the same units. So make sure that you can prove to yourself that they do, and that Bernoulli's equation is true. So that's all I want to talk about now. Make sure you read through all the examples and be ready to talk about some of the examples in class.